So, in last class I have discussed about the sensitivity, current sensitivity as well as charge sensitivity of a suspension type of moving coil galvanometer. So, now we will perform the experiment using this galvanometer. So, this is the setup, experimental setup for 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 this experiment. So, this is a galvanometer, this suspension type galvanometer. So, as I told, this coil, rectangular coil is hanged, is suspended by a fiber rope. So, here inside you can see, this this is basically this magnet, this basically permanent magnet, and pole piece, you can see this pole piece is also this concave type pole piece, and inside pole piece this rectangular coil, you can see rectangular coil, and that's this coil is suspended using this rope, and on top of rope this one mirror, you can see this round one mirror is there, is attached. As I mentioned, this there will be mirror on the suspension coil, and now this light is falling. This is the light scale arrangement. This is the light scale arrangement. This light from here it is coming and falling on this mirror, and this reflected one is coming and falling on the scale. So, now at the moment this you can see this round, you can see here this round spot, light spot. So, that is that we have kept at 0 position, we have kept it at 0 position, right. So, so if any rotation of this coil, then mirror will rotate, and then this spot, light spot will move on the scale. So, that is basically that displacement of this light spot, that if we measure that one, and if we know the distance from this scale to this mirror, then basically we can find out the angle of rotation. Okay. So, this is the galvanometer, and if any rotation of this suspension coil with some angle theta, so that we can measure using the light scale arrangement. Now, what we want to find out? We want to find out the current sensitivity and then charge sensitivity of this galvanometer. So, current sensitivity, what is the current sensitivity? So, di by d theta. So, that is basically you can write I by theta. So, eta, so I will just tell you, I will tell you that eta current sensitivity is basically I by theta equal to some constant C by Na B. So, now what will happen? This I is proportional to theta, this proportionality constant is this eta. So, that is the current sensitivity. So, now I have to pass current through the coil of the galvanometer. Then what is the deflection of this coil, that I have to measure. So, I need arrangement for passing current through the galvanometer, and then using the light scale arrangement we will measure the theta, right. So, basically when mirror will be rotated by theta, this reflected light. So, this is the initial light at 0 position. Now, if mirror rotate by theta, so this reflected one will rotate by 2 theta. So, this displacement, if it is small d, and this distance mirror and this scale distance is capital D. So, then tan 2 theta will be equal to d by capital D. So, theta, so this will be basically not not d. So, it will be basically theta. So, theta will be equal to d by 2 capital D. Okay. So, capital D we have to measure. So, generally it is given the student, or you can measure using the meter scale, and of course, this small d you have to measure. That will I will show you. Now, theta I will be able to measure using this light scale arrangement. So, now I have to pass current to the galvanometer, and for that current, what will be the deflection that I have to measure. So, for that, this is the circuit. This is the circuit for passing current through the galvanometer, right. So, this is a simple circuit. Now, you see you have galvanometer, right. So, I want to pass current through the galvanometer. I want to pass current through the galvanometer. So, in series we have added one resistance box, that is R. Okay. Now, if power supply is connected here, so then current will flow through this. Now, this current passing through the galvanometer, that I can control. Just changing the resistance R. From this box, if I change the resistance R, I can vary the current passing through the galvanometer, right. So, but here I have not added this power supply directly. So, here what we have done, so I have used one commutator. Reason is that this I want to just change the direction of the current. Okay. So, I want to change the direction of the current, so that's why we have used commutator. So, in commutator you know this okay, there are 4 option for connection. So, this diagonally opposite, these two are connected here, okay, for this main circuit, and this battery is connected to the other diagonally other two end. Okay. So, now when you will just close these two, then whatever the direction of the current, so you can reverse the direction of the current if you just reverse, if you open these two and close these two. Okay. So, this way just we can just reverse the current. So, this is the standard procedure to reverse the current in the circuit. So, that we have added here. Okay. Now, here basically I have to add the power supply. So, again means I need power supply between these 2 points, and or EMF between these 2 points. Now, here I have a battery. So, it has fixed voltage EMF. So, that EMF is E. So, now this I am not connecting with this one directly, but rather I have used this voltage divider. I can choose the voltage, I can choose and vary the voltage between these 2 points. So, that is why I have used the voltage divider circuit. So, this is the standard circuit. You see, this is the battery, this is the just one circuit breaking key. Okay. If you close it, then the circuit is closed. If you just open it, circuit is open. So, this battery is now I have connected this resistance box Q in series, and another resistance box, or just resistance, simply resistance P. Okay. So, this you can take as a circuit, this you can take as a circuit. So, current will flow through this circuit will be E divided by total resistance Q plus P, E divided by Q plus P or P plus Q. Okay. So, this will be the current flowing through this circuit. Now, then voltage drop across this resistance will be into P, I into P, resistance P, Okay, so this will be the voltage drop across this one. So now this will act as a voltage source for this circuit. If I connect this way, so this voltage drop, that is now EMF across this P. So this is now power source for this circuit. So this the EMF or voltage for these 2 points. Okay. Now current will flow through this circuit through the galvanometer. So this I can write IG, current passing through this galvanometer. So this voltage divided by total resistance in this circuit. So total resistance in this circuit is R plus G plus basically P. P is the one can take as the internal resistance of this one, but we neglect P because this P will keep it very small compared to this resistance R. So condition you can only neglect, condition is you have to keep P very small compared to R. So this assumption we have made, so during experiment that assumption we have to follow, right. So that's why we have neglected this resistance P. So we have taken total resistance in this circuit is R plus G. So this potential, this voltage EMF divided by this resistance. So that will be current in this circuit, that will be the current in this circuit, that is IG. So basically then E P divided by P plus Q into R plus G. So that is the current passing through this galvanometer, right. So now then eta is basically I by theta. So I is this one into 1 by theta. So that's what I have written expression. So here you see so here I can write basically R plus G equal to eta I can take here, R plus G equal to EP by P plus Q I have to write, yeah, P plus Q into eta into 1 by theta. Okay. So I can, because the G is not known to me, the G is the basically the resistance of the galvanometer, that is not known to me, so I want to avoid it. So that's why for a particular value of R, so that is R1, so deflection I will get theta 1. For another value of R that is R2 plus G, I will get deflection theta 2. So this is 1 by theta 2, right. So if you just take difference between these two, so R2 minus R1 G will go. So I will get EP by P plus Q into eta into, I think I have to put bracket, okay, into this. Okay. So basically this expression is now not having the G. In this expression all are known to you because R is known, P is known, then Q is known, E is known, okay. Then theta you have to measure. So for different, so our task is basically we have to vary R and measure the theta. Then we'll plot graph 1 by theta versus R, 1 by theta versus R. So this you can write R2 minus, okay, 1 by theta 1 minus 1 by theta 2 divide by R2 minus R1, okay, and then eta I will take this side. So eta will be equal to EP by P plus Q into 1 by theta 1 minus 1 by theta 2 divided by R2 minus R1. So that is basically, if you plot 1 by theta along the y-axis and along the x-axis r, and if you do the experiment for few r, so for different r, what is 1 by theta, that I will plot, and I will plot, and this from the slope of this curve basically will give you this 1 by theta 1 minus 1 by theta 2 divided by r2 minus r1. So then other value are known to you. For the this we are not varying, this we are keeping fixed, okay, only we are varying r, and then if we vary r, then Ig will be different. For different Ig, theta will be different. So we will measure theta for different r. That's what our task. Then we will find out tau, eta. So that will be the current sensitivity. If I know the current sensitivity, so then I can find out the charge sensitivity, because eta is already known from this experiment, and then only I have to measure the oscillation time period for the oscillation of the curve of the coil, okay. So that T I have to find out, then I can get this charge sensitivity. So our experiment is basically for different R to different R, I have to measure theta, okay. Then I will plot it and get this slope, and then I will get eta, and then I will measure the T time period, then I will get the K, charge sensitivity. So now this circuit I need. So I will show you this circuit as I showed here in my sketch, in my drawing. So here just compare with this one. So so let me show you this this part first, okay. This circuit for the galvanometer part, okay. So this is the commutator, right. Okay, it has 4, as I told this, it will have 4 connection option 1, 2, 3, 4. Okay. So this is kept closed, but just one should keep, because this circuit is kept break. So that's why if we put here also, there is no problem. So this commutator. So now you see this, as I told, diagonally opposite. So diagonal opposite, take this one and the other one. So these two is connected with the galvanometer through a resistor R. So start from here, come. This is the R box, resistance box, R resistance box. So this resistance is in series with this galvanometer. So I think this is, yeah, this is in series with this one. This is coming here, okay. So this that resistance box is in series with the yes, here it has come. So opposite, diagonally opposite connection. So this circuit contain the resistance box R2 R and this galvanometer in series, right. Now again here, this diagonally opposite these two, I have to connect the battery, right. So this arrangement, as I told, is just for this is just for the for reversing the current in the opposite direction. So now battery. So here as I mentioned, this we will connect just across this P, because this whatever the voltage drop across the P, so that will be taken the power for this EMF for this part, okay. So this 2 is connected across the P. So this is P, so this is constant resistance, very small resistance. How much it is written? It's is ohm, yeah, very small, there is a 2 ohm, this is the 2 is written 2 ohm, okay. So, this 2 ohm resistance, okay, that is P, that is fixed, okay. So, that is connected, this P is this one is connected across this P, okay. Now, this P and Q, this box is Q, P and Q is in series with the battery, So, here we have used this battery, okay. So, just yeah, this basically how much, what is the voltage is written here, yes, 1.5 volt, 1.5 volt. So, basically 3 volt. So, these two batteries are there 3 volt. Okay. So, now you see this start from the one end of this battery, one electrode of the battery. So, if I start from here, so this is going to this resistance box Q and then coming following this one, then passing through this P, here, just break Q we have used, and it is coming to the other end. Okay. So, this is a one circuit, battery circuit. So, current in this battery circuit we can vary, just varying the Q, because here P fixed and this one also fixed. So, varying the Q we can vary the current. Okay. So, now voltage drop across this is this current in battery circuit into this resistance P, this is constant. So, varying the P, basically I can choose voltage drop across this P, which will be the voltage source for this galvanometer circuit, right. So, now what is the experiment I have to do? As I told, just I will vary the R and measure the theta. So, that is the experiment I have to do. So, now at the moment here we have set this the resistance here. This Q is here, I can see this is 1000 plus 500, 1500 ohm, this Q that I have to note down, and here this P is 2 ohm that I have to note down. Battery voltage E is the basically 3 volt that I have to note down. Now, here R I kept is the value is 1000, here also a value I kept is the 1000 that I have to note down. Okay. So, now light scale arrangement, okay, when no current is passing through this circuit. So, it is at 0 position, the spot, light spot at this 0 position. So, now what I will do? I will pass current through it, and for that current, what is the deflection theta that I have to measure? Basically, here I have to measure the small d, then from theta equal to small d divided by 2d, I will find out the theta. So, that theta, so basically R versus theta or 1 by theta, that data we will get. So, now let me show you just experiment. So, I just close these two. Okay. So, current will flow in a particular direction, then I will make it opposite. So, current will be reverse. So, that we will do after this experiment, after this data. So, now you see this still it is at 0 position, this still it is at 0 position, because current is not flowing through it, because these are so this key that is open, that key is open, right. Now, you see just when I will close it. So, then let me just close it and then see. You see now spot is come here, spot has come here. So, that reading I have to take. What is the reading of the spot? What is the reading of the spot? So, this 10. Okay. So, what is the maximum value that I have to take? Okay. So, is the 10. Okay. Is the 10. Okay, it is coming at steady state. So, okay. So, it was at 0, sorry, it was at here. So, that 0 position. So, I have to take this top scale, it is 10, 11, 12. So, 12, 12 point, I will take this 12.5, I will take this reading 12.5. Okay. So, for a particular this value of R is 1000 ohm, I have to note down for that this small d is 12.5. Now, I will reverse the current, I will reverse the current. Okay. I will reverse the current. Actually, I should take it. So, I should break this circuit. I should take it to 0 position. I should take it to 0 position. Okay. So, so this across this galvanometer, we should keep option this one key to short it. So, that will come to 0 position very quickly. So, just I will make it short. So, it will come at 0 position. Okay. So, basically this way we are introducing very high damping. I will explain sometimes. So, then it is damped and come back to the 0. Yes, now you see this just it is. So, it is just 0 is top, on top is 0 is written, on top is 0 is written. Okay. So, we are taking this scale, this top scale. Okay, 0, 1, 2, 3. This side 1, 2, 1, 2, 3, 4, 5. Okay. So, now I will reverse the current. Okay. So, that means I have to when I forgot it was where it was, here or here. Anyway, let me try. Okay, in which direction it is going, then I have to reverse, but I do not remember it was this side or it was here. I think it was there. So, I have to just reverse it. So, wherever if it was there, so I have to take this other way or vice versa. So, now I will just close this one. Okay, this circuit. So, you see where in which direction it is going. Oh, okay. So, it has gone to that direction. That means this was earlier position. Now, I have to reverse this position. I have to reverse this position and bring it back to this just to the 0 position. So, I have to shorten it. So, basically these two just I am connecting here. Okay. Okay. So, introducing high damping so that it will come back to 0. So, hopefully it has come back to 0. Yes, it has come back to 0. Okay. It has come back to 0. Now, I have put in reverse direction. Okay. And then I have to close it. I have to close it. Then current will flow. You see. Yes. Now, deflection is in opposite direction. So, here I have to take. So, let us allow to come at steady position. Okay. So, as I told, we should take maximum deflection. No, that is not correct. We should take at this steady position. So, now steady current is flowing. For that, what is the deflection that we have to take? So, this reading is now again 10, 11, 12, 12.5. Okay. So, it is a perfectly symmetrical. So, just reversing current, that side I got 12.5, this side also I got 12.5. So, basically mean of these two we have to take. Okay. So, it is a mean is 12.5. Okay. So, for this resistance R, that is 1000. So, I got small d, that is 12.5, and corresponding theta. So, I know this distance, I know the distance, or you have to measure generally is supplied. So, so if you know this capital D, then you will find out the theta. Okay. So, R and then corresponding theta, and then 1 by theta, you can note down, you can calculate. So, now this is for 1000. Now, I will add, so I should break circuit, okay. Then take it at 0 position, take it at 0 position, okay. Yes, it has come at 0. So, now I will do the experiment for, I just added 500 more. So, it is now 1500. Now, R is 1500. Then again I will repeat the experiment. So, you see what is the deflection that I have to find out. What is the deflection I have to find out? So, let us come to the steady state, steady deflection. So, that I have to, so basically I have to note down this value and then I will reverse the current, and then other side deflection I have to see. So, then average of these two deflection will take, okay. So, now reading you can note down, I think is the 9 or 9.2, you can note down 9.2, okay. So, so just reverse the current, I should break it, because we should not pass current for longer time, then take it to the 0, right. So, just now reverse the current, again repeat the experiment and take the reading. So, this theta you will get, or 1 by theta you will get for resistance R equal to 1500. Next I will do for say more 500, I will take add this resistance. So, for 2000, R equal to 2000, I repeat the experiment, R equal to 2500, R equal to 3000, just I will repeat the experiment. Now, in this experiment, so we assume that P will be very, very small compared to R, and that is what P is 2 ohm, whereas this R we are taking in 1000 ohm, 1500, 2000, okay. So, it is really P is very, very small, that is why we neglected that one. Now, just you plot the graph 1 by theta along the y axis versus this R, okay. So, then from that curve basically find out the slope. So, here just we did the experiment, I will just show you, I have the plot, I think coefficient is, yes, basically you have to plot this 1 by theta versus this resistance R, okay. Then basically you are getting this type of state line, Now, yes, so just find out the gradient, you know how to find out the gradient, just choose two point and then a straight line. So, basically you are getting here from, or just from here itself, one is take as R1, another is take as R2, corresponding 1 by theta 1, 1 by theta 2. So, you will get basically 1 by theta 2 minus 1 by theta 1 and corresponding R2 minus R1, and then slope we find out this by this. So, that will be the slope that you will use for your experiment. Actually, we did for real data we have plotted here, and one has to find out this graph, the slope from this graph. So, and then there are some, so then you can find out eta, okay, that is basically current sensitivity. Now, for charge sensitivity what I will do? So, just I have to measure the oscillation of this coil. So, basically I have to find out the oscillation of this light spot, right, time period of this light spot, because this light spot, this oscillation is same as the oscillation of this coil, is related with the mirror and that is reflected light. So, for that what I have to do? So, this some charge. So, some charge momentarily some charge I should pass through this galvanometer, right. So, what I will do, just I will close and then again I will open it, okay. Then it will start to oscillate. So, so let me start. So, I closed it and then I just open it, okay. Now, I have to take stopwatch. So, now I have to just start and then count this number of oscillation, okay. So, if I start from here, so then 1, 2, okay. So, you will get few 2, 3, 4, 5 you will get, and for that you will get time from here. So, stop it and then just this time divide by this number. So, that will be basically time for a one oscillation. So, that is the time period, that is the time period, and T is known to you now. So, T here you have measured from here. So, now T is known to you. So, that is K, that charge sensitivity is basically eta into T by 2 pi. So, T you will get from this measurement, and then you can calculate the charge sensitivity, okay. So, I think rest of the things, error analysis and this discussion precaution, that you should do yourself for this experiment, and sometimes we will discuss in our tutorial class also. So, this is a very nice experiment. It is simple, but one can learn lot of things from this experiment about the mainly about the galvanometer and its sensitivity, right. Figure of merit, which is basically the current sensitivity, and one has to understand the basically circuit, the simple circuit, but what is the purpose of this different arrangement, that one should understand, then things will be very easy, and one should also understand the working formula, how it has come, what are the assumptions, like in this experiment P we have to take very small compared to Q, that condition has to fulfill during the experiment. So, that also we have checked. So, these are the precaution one has to write in precaution or discussion, you should mention these points, okay. So, I think I will stop here. Thank you.